What if I told you that the entire future of artificial intelligence, all of it, hinges on one single machine? No, it's not some super advanced software, it's not a giant data center. It's a physical thing, a piece of hardware so complex it represents the absolute peak of human engineering. And we're about to peel back the layers on what makes it tick.
So let's just start with the price tag, because it tells you a lot. A single one of these new machines, it costs around $400 million. Let that sink in. That makes it by a long shot the most expensive machine tool in human history. And that price, well, it's just a hint at the mind-bending complexity we're about to get into. You know, the thing that's so wild about this machine is the sheer paradox at its core. I mean, on one hand, it is colossal. It's bigger than a double-decker bus, and it's so heavy it takes 7 Boeing 747s just to ship all the parts. But on the other hand, its entire job is to work on a scale that is basically impossible to imagine. We're talking about printing transistors 10,000 times thinner than a human hair. The accuracy you need for that? It's like standing on Earth and aiming a laser pointer to hit a coin sitting on the surface of the moon.
So yeah, that brings us to our first section. We're going to try to wrap our heads around the physics and the engineering it takes to even build something like this.
Okay, so what is this thing? Officially, it's a High-NA EUV lithography system, and that's just a fancy way of saying it's the most complex tool humanity has ever built. High-NA means it could see incredibly fine details. And here's the kicker. Only one company on the entire planet, a Dutch firm called ASML, has figured out how to make them. They have a complete 100% monopoly.
So what does it actually do? Well, you can think of it like the world's most advanced printer. It uses a super precise beam of light to etch these unimaginably tiny blueprints for transistors onto silicon wafers. Every advanced microchip in the world, the one in your phone, your computer, the ones running AI, they all have to pass through one of these machines. Without it, the modern world just stops.
All right, now we're going to go deep inside the machine's core. We're going to where the magic happens, a place where they literally have to forge light from scratch.
Okay, so here's the first huge problem they had to solve. The special type of light you need for this job is called Extreme Ultraviolet, or EUV. It's incredibly powerful, but EUV light that's absorbed by basically everything, even air. So the entire inside of this bus-sized machine has to be a near-perfect vacuum. Just creating and maintaining that space is a ridiculous engineering challenge all on its own.
So inside this vacuum, this insane little dance happens. First, zap. A tiny droplet of molten tin, just 30 microns wide, is shot into the chamber. Then, a smaller laser hits it, flattening it into a perfect little pancake. Then, boom, a massive high-power laser absolutely vaporizes that pancake, turning it into a super hot plasma. That plasma gives off a brilliant flash of EUV light. And now for the craziest part. This whole sequence repeats, with perfect timing, 50,000 times every single second. And just to give you an idea of the power we're talking about, one of the lead engineers described it like this. The laser they used to vaporize the tin is so powerful it could cut through steel. And when it hits that little droplet, it creates a plasma that is hotter than the surface of the sun. And it does that 50,000 times a second. It's just wild. Now that we've seen the physics, let's talk about the hardware, the physical components that make this all happen. These aren't just off-the-shelf parts. Each one is an engineering marvel that pushes the absolute limits of what's possible.
So after that flash of light is created, you have to catch it and focus it. And since EUV gets absorbed by lenses, they have to use mirrors. But these aren't your bathroom mirrors. These are made by the German optics masters at Zeiss, and they are, quite literally, the flattest, most perfect surfaces ever created by human hands. To put that perfection into perspective, Zeiss has this incredible analogy. They say if you could scale up one of their mirrors to be the size of the entire country of Germany, the biggest bump, the biggest imperfection on its surface would be less than 1 millimeter high. That's the kind of insane perfection we're dealing with.
But chasing that kind of perfection creates all new problems. For example, the new optics are so huge they can only print half a chip at a time. So what's the solution? Something called in-die stitching. They literally print one half of the chip design, then print the other half right next to it and stitch them together on the silicon. And the alignment for that stitch has to be perfect down to less than a single nanometer.
And the challenges just cascade from there. The special chemical coatings on the wafers, the photoresists, had to be totally reinvented. The tools used to even look for mistakes, a field called metrology, now have to use electron beams because the defects are too small for light to even see. And at this tiny scale, you even have to worry about random quantum-level errors, so-called stochastics, which requires massive AI models just to predict and avoid them. Every single piece of the puzzle had to be pushed to a new extreme.
So why? Why go to all this trouble? Lasers, vacuums, perfect mirrors. What's the point? Well, this is where it all comes together. This is how this incredible machine connects directly to the AI revolution that's changing our world. It really starts here. The whole AI boom, ChatGPT, self-driving cars, all of it. It all runs on these incredibly dense and powerful microchips, the kind designed by companies like Nvidia. And the secret sauce for these AI chips is just cramming an unbelievable number of transistors into a tiny space. We're talking billions and billions of them. And to do that, you have to print the features on the chip at a resolution of 8 nanometers or even smaller. I mean, we are right at the edge of physics here.
And so here's the bottom line. To print things that small, with the speed and the quality you need to make millions of them, there is only one type of machine on planet Earth that can actually do it.
The ASML High-NA EUV system. Without this specific machine, the advanced chips from Nvidia, from Apple, the chips that power the AI industry, they couldn't exist. It's that simple. This machine is the single choke point, the one device that makes the entire AI revolution possible.
Now, because this one machine is so incredibly critical, it's become a major piece in the game of geopolitics. The technology is now under very strict export controls, which means ASML is blocked from selling its most advanced systems to countries like China.
And get this, the strategic value is considered so high that these machines are built with a remote kill switch. The thinking is, in a worst-case scenario, like an invasion of Taiwan, where most of these machines operate, ASML, from their headquarters in the Netherlands, could remotely shut them all down, instantly turning the world's most advanced factories into nothing more than very, very expensive paperweights.
And that leaves us with a pretty heavy final thought, doesn't it? This machine is an absolute marvel of human ingenuity. There's no question. But what does it really mean for our future when the engine driving all of our progress is a single $400 million machine made by just one company, in one country, with a kill switch?